Hello, everyone. My name is LKallab. I am the technical manager of the research and the development projects held in Open. Open is a French digital services firm that assists companies, our client, in their digital industrial transformation. Recently, we have been collaborating with the OpenCEMS chair attached to the University of Pau, also located in France, on several R&D projects related to data management and analysis in connected environments. Now, among our work together, today I'm going to present you the WoR Ontology, standing for Web of Resources. Now, don't be afraid, I'm using the term WoR in its good sense. So it's a model that is used to describe web services or web resources that are provided by connected environments. So this is the outline of my presentation. I'm going to start with an introduction in order to define the context of the work. Second, I'm going to pass to the motivating scenario, where we're going to show you what were the motivations behind the work. The part 3, we're going to see several different works that are related to our research domain, along with our limitations. In part 4, I'm going to present you the main sections of the WoR model, and we're going to evaluate this model according to 2 aspects in the 5th part, the performance and effectiveness, and finally a conclusion with some future works. So the Internet of Things, or IoT, is a term that encompasses a wide range of objects, such as smart devices, that are embedded with sensors, software, electronics that are connected to the internet in order to collect and share data. Now, with the heterogeneity of objects, it is quite challenging to have a seamless communication that guarantees an interoperability with these objects. And this challenge is also appears also in applications to applications interactions, as applications today are developed on different platforms and based on various programming languages. So in order to tackle such challenge, the web has emerged as a technology to guarantee the communication between these applications and objects despite their differences. And since then, the web has become the major lead of communication platform that led to the emerging of what we call today the Web of Things, or WOT. Now, in the web context, each object, which can be stationary, have a fixed location, or mobile, and each application or platform provides their functions through what we call web services. Now, web services by definition are self-describing, self-contained modular components that can be published, located, and invoked across the web. Web services today can be implemented through several technologies. We have, for example, SOAP, which is a messaging protocol that allows the exchange of XML data between web services. We have also XML RPC, standing for remote procedure calls, and we have REST, which is an architecture style based on several principles. Now, REST recently has become the most used solution for implementing web services due to several factors. Among them, its simplicity and ease of use, making service integration cost-effective, its support for different data formats other than XML, for example, JSON, which is a more lightweight format comparing to XML. This is a very important thing to consider, especially in the IoT world, where we have tiny, small objects that can communicate, and its support for caching for better performance and scalability. So today, more and more objects and applications provide their functions as RESTful web services that follow the REST architecture style principles. Now, these web services should be defined in a way it allows them to be largely adopted for interoperability purposes. And the web alone does not solve the interoperability issues. In fact, it is well acknowledged that semantic web technologies hold the potential of achieving data and platform interoperability. And this is done by describing and sharing knowledge on web services using unambiguous and machine understandable vocabularies in order to give or attribute the same meaning, the same semantics to the shared data. So one of the main building blocks of the semantic web technologies are ontologies, which provide a common and comprehensible vocabulary for publishing data through a formal explicit specification of a domain. In fact, they facilitate knowledge sharing between systems, allowing the interoperability not only on the syntactic level, but also on the semantic level. Now, in the state of the art, there have been many IoT web models that have been defined to represent IoT web domains. And these models have been defined for several purposes, different purposes, among them to represent a specific knowledge domain in a machine understandable way, so that things along with their services or functions can be published, discovered, can be aggregated, and can be remotely accessible. However, these models have several limitations. For example, they focus more on describing the services that are exposed by objects and neglect or do not consider the services that can be exposed by applications or platforms. This reduces the expressive power when we're going to query and explore the connected environment. Second, they lack in considering services links, which is an important criteria to consider, especially when composing services together when no single service exists in the connected environment that can answer user requests. So it's important to compose services together, and semantic links can facilitate such composition. Third, they do not describe composed services in the sense that they do not describe the behavior of a composed services. And if they do it, sometimes they do not store this description of the behavior in their model. So if we're going in some demands, we need to have composed services, we need to re-execute again the discovery, the selection, and the composition process in order to have these composed services. And finally, they do not describe virtual services. Now, virtual services are services that can simulate the behavior of non-existing physical devices. So imagine we are in a connected environment, and at some point we need to have a device. However, this device has a high cost. So what can we do? We can, based on several algorithms and applying few calculations, simulate the behavior of this non-existing physical device. So we can have what we call virtual service. So virtual services are supposed to be added value services beside the composed services. Now, in order to address all of these limitations, we propose in our paper, in this presentation, the WoR model, Web of Resources. So WoR stores and integrates resource specifications related to heterogeneous objects and applications. It eases the discovery, selection, and composition of the exposed resources, basically through using the semantic links, and provides reasoning means to discover new information. This is one of the main purpose objective of using ontology, and allows future extensibility and adaptation. We motivate our work through illustrative scenario that we illustrate in the OpenCEMS platform, which is a web platform that provides solution for energy data management in connected environment. So the platform allows to connect objects, smart devices, as well as applications. And these objects and applications can expose several resources for either collecting on-site data, for example, temperature, humidity, etc., for pre-processing data, for example, to convert temperature values from a unit to another, and for analyzing data, for example, by applying machine learning algorithms to, for example, predict the energy demand. So let us consider the case of a facility manager that wants to predict the energy demand of this shopping center for a specific building for the upcoming, specific floor of this shopping center for the upcoming 2 days. So in order to monitor the energy predicted data, and why not to establish plans for energy supply and demand. So in order to fulfill his needs, he has to know what are the resources to select, how they can be linked together in order to have this composition. So he has to collect the external temperature, applying few pre-processing, for example, to convert the temperature values from a unit to another. He has to collect internal temperature data, external humidity data, and all of these data will be passed to the energy consumption data prediction to have the predicted results. However, due to the heterogeneous numerous resources that can be provided by the shopping center, along with the different functionalities, where some of them are the same, we can have many resources that can provide exactly the same function, along with their different characteristics in terms of time, response time, cost, performance, availability, it is quite challenging and not easy for the facility manager, non-expert, to know what kind of resources should he identify and select. So what we need here is to have a unified description model that describes all of the functionalities and non-functional aspects of resources in not only a human comprehensible way, but also in a machine readable vocab. So in the state of the art, we have analyzed several works and compared them according to several criteria that we categorize in 3 categories. The first category, thought of model, it refers to the ability of the model to describe several kinds of services. The ones that are exposed by objects, the ones that are exposed by applications, elementary services, composed services, virtual services, and the aspect category is very important. It facilitates, in fact, the exploring of the connected environment and facilitate the comprehensibility of the behavior of these services. The second category, expressiveness, it refers to the ability of the model if it supports the criteria to represent more a service. For example, its provided function, their input-output, its location whenever it is exposed by object, and of course, the links, semantic links. And finally, the third category is service quality. It refers to the ability of the model to support service quality aspects on 3 levels. Physical refers to the quality of the object, for example, the Bluetooth range. Network refers to the quality of the communicated data between objects and applications. And finally, the application level refers to the quality of the function provided by the service, for example, performance, usage, etc. So as we can see, none of the existing models can support or cover all of these criteria until we define WoR model. So WoR model is an extension of 2 main ontologies, which are HSSN and SOSA. So HSSN is an extension of the semantic sensor network. It models the hybrid semantic sensor networks that includes stationary mobile sensors, scalar multimedia properties, and infrastructure devices as platforms where these sensors are deployed. The second ontology is called SOSA. So this ontology models the interaction of the entities that are responsible of the act of observation, sampling, and actuation. So a part of these ontologies, we define the new concepts and new relations to cover the required criteria that I just previously explained. So as we can see in the figure, we have a resource, the concept. It can be elementary resource, virtual resource, and a composite resource. A composite resource can have a behavior that is represented through the concept workflow, which has component, and each component represents a resource. And as we can see, a component can have different orders between them. It can be in parallel or in sequence. So this is to describe the behavior of each composed resources. This part here, we can see that we have the quality of resource on 3 levels: physical, network, and application. Each resource can provide operations. Operation can have input parameters represented through the relation of expects. An operation also can have output parameters represented through the returns relation. Now, if we look carefully on the concept resource, we can see that we have defined several reflexive relations. So for example, the same as, so this is a semantic link that you define between service and resources, so that when each or two resources can have exact the same function, they are linked through the same as relation. So this is a very useful link because let's suppose we have a composition. During the execution of the composition, if one of the resources is no more available, we can use this link, same as, to know what are the other resources that can be available to substitute this unavailable resource. The follows relation is another example of a semantic link that we defined, and this link relates two resources having dependent functions. For example, we cannot convert temperature values from a unit to another unless we collect temperature values. So these two resources will be linked through the follows semantic link, and which will facilitate the discovery process and selection during composition. So in order to evaluate our WoR model, we basically applied two aspects of the evaluation: effectiveness and performance. So in the effectiveness evaluation, what we did is we verified whether the concepts and properties that we defined in the model can cover several objectives in terms of exploration of the connected environment, service discovery, selection, composition, and execution, and of course, the criteria that we have defined earlier in my presentation. So what we did is we defined several lists of useful queries that can aid the user to explore, to identify, to select and compose services. And as we can see, we covered all the required objectives as well as the criteria. So now performance evaluation. So the performance evaluation was based on the execution of several queries that we picked from the list of these queries here, and computing the response time of the WoR model in different resource graph configurations, while varying the number of resources, while varying the provided function of resources, while varying the number of devices exposing collection data resources along with their distribution in different number of locations, and while varying the number of resources involved in a composed resource. So as we can see from the generated graphs, we have a promising positive linear curve in all of these graphs, which means that the response time increases linearly. And as we can see, it is a constant increasing with the increasing number of variables that I just mentioned. So the result highlights also that the increasing number of resources along with the increasing number of devices collecting data affect more the response time comparing to the other variables. So to recap, in this paper, we have defined what we call WoR ontology, standing for Web of Resources. It is used to describe the services or the resources provided by the objects and the applications exposed by connected web environments. It includes the functional and non-functional aspects of the resources, as well as their composition features. It reuses several existing known IoT-based models, HSSN and SOSA. Its effectiveness and performance have been evaluated in different resource graph configurations, which have shown promising results. Now, as future works, we aim to first test word clarity by verifying whether the names or labels used to describe the concepts, properties, are not ambiguous for users, experts or non-experts. We seek also to test word consistency by checking if the added concepts or properties generate inconsistencies within the ontology structure. And finally, we aim to use the proposed solution in real web-based environments, because now currently we have been using in simulated environments, such as the web platform OpenCEMS, and of course, an ongoing web-based project provided by my company, Open. So these are some of the references that we integrated in the paper. Thank you all for your attention. Ready to receive your questions.
Thank you. Do you have some questions? No? Yeah, I think you must come here.
So thanks for the presentation. The model looks very extensible. So is this something that you plan to use in a decentralized context? For example, adding devices in real time to the semantic graph as they are discovered, or is it more of a static model?
No, it will be dynamic, of course.
Yeah. Okay.
Exactly. And this is the purpose why we use ontologies.
Yeah. Okay.
Thank you.
Okay, thank you.